Hello everyone. Today we will discuss a design of flexural members. In previous classes we have discussed about analysis of flexural members. So in flexural design we will be having two different stages. So that is one is preliminary design and another one is final design. In preliminary design it is mainly concentrating on the design of cross section of the member, cross section dimensions, then what is the area of steel required, what is the area of cross section required, and all those things. And in final design we are going to design the member and we are going to check for the eccentricity and pre-stressing force, pre-stressing force on the concrete as well as on the tendons. Those things we are going to discuss. So let's start with primary design. In primary design totally we will be having 9 steps. So in first step, first we need to select what is the property or characteristic strength of the material we are using. That is, it is a characteristic strength of concrete, and what is the pretensioning steel, what should be the strength of pretensioning steel, that is FP. FCK is the characteristic strength of concrete and FP is the tensile strength of tendons that we need to select. Then in second step we need to calculate the depth of the beam. So to calculate the depth of the beam we have formula. It should be 0.03 root of m to 0.04 root of m. Based on the architectural requirement we can choose the depth. So here m is the total moment due to self weight. Then step 3, type of section, whether we need to go for rectangular section or flanger sections, we need to decide. So if it is rectangular section, the width of the section should be half of the depth. It is just assumed, we can change with respect to requirements. Then in next step, after calculating width and depth by using density of concrete, we can calculate or we can estimate the self weight of the member, or if it is not given directly we can take 10 to 20% of the live load given. Then moment due to self weight we need to find out. Then moment, total moment, it includes moment due to self weight as well as live load. So moment due to live load we will denote it as ML, moment due to self weight or dead load we denote it as MD, and total moment it is MT. Then estimate the lever arm. So in lever arm is nothing but it is the distance between the centroid of the section to the position of the compression force. In first module we have discussed about this. So to calculate that lever arm we are having two conditions. If the dead load moment is more than 30% of total load, for example if you have 100 kilonewton meter as the total moment, your dead load is more than 30 kilonewton meter. So in that case lever arm will be 0.65 times of h. Here h it denotes height, depth of the section. Instead of h we can denote it as d. And if the dead load moment is less than 30% of total moment, it is 0.5 times of h or depth. So next, estimation of effective pre-stress. What should be the effective pre-stress we need to apply for the particular section. So if dead load moment is more than 30% of total moment, then for that we use MT by Z. If it is less than 30%, ML by Z. So if dead load is more than 30%, we will consider total moment. If dead load moment is less than 30% of total moment, we will consider only live load moment. Next step, FPE. So FP, it is the material property we have considered. We need to consider it as some factor of safety. So for that we are going to consider 0.7 times of FP. That is, if you have selected 1000 Newton per mm square as the strength of tendons we are using, we need to consider 0.7 times of 1000 as the effective stress, pre-stressing stress, and for that effective pre-stress we need to find out what is the area of steel required. Effective pre-stressing force we have calculated, and effective pre-stress for the selected tendon, it is depend on our selection. Based on those two values we need to find out what is the area of tendon required. Then check the area of cross section. So we have provided d by depth and width for the section. We need to check whether it is safe enough or not, or we need to revise the section. So for that we will be having different conditions. In design part we will discuss about that, but for that formula is compression force by area should be equal to P, that is effective pre-stress by area, average stress in concrete. So this is about preliminary design. So in final design, if you come to final design, we are going to consider three different cases. So here I have given final design for type 1 member. So as per IS 1343/1980, it defines as three different types of flexural members. So type 1, type 2, type 3. As per your syllabus you have only type 1 member, so I have mentioned it as final design for type 1 member. So first we should know what is type 1, type 2, type 3, why we have divided it. So in type 1 you can see no tensile stress is allowed in the concrete at transfer or under service loads. So we know concrete is strong enough in compression, but it is weak in tensile stress. So at transfer, that is when you apply the pre-stressing force, there will be upward deflection. So in that case, upper fibers will be under tension and the lower fibers will be under compression. So when the beam gets deflection downwards, then upper portion will be under compression and lower portion will be under tension. So here no tensile stress is allowed in concrete at transfer or under service loads. That means when you apply the pre-stressing force, you need to maintain that there is no portion of this cross section should be under tensile stresses. That means you are applying the pre-stressing force such that all the tensile stresses in the concrete should be zero. In such way you are going to design. So in type 2, tensile stress is within the cracking stress of the concrete. So first you are going to apply the pre-stressing force, it will be under upward deflection. Then on applying the live loads, it will come to downward deflection. So in that case, at certain location, certain instant, when it reaches the maximum deflection, it starts cracking. So the moment at which the cracks start, until that tensile stresses are allowed in the concrete. Next, in type 3, tensile stress is such that the crack width is within the allowable limit. Say for example, the allowable cracking width is around 5 mm. So you can increase the tensile stress in the concrete up to the crack width limitations. So when downward deflection happens, at certain stress levels the crack will develop. When you further increase the stresses, the cracks will become wider. So that widening of the cracks will be limited to 5 mm. That way we can design. So these are the three conditions where we have divided the types of the members. So type 1, type 2, type 3. So as per syllabus we have only type 1 and we will discuss about the same. So in type 1 design we are mainly having 4 steps, 4 different steps in the design of type 1 member. So first we are considering the condition that moment due to dead load is less than or equal to 30% of the moment due to total load. MD is less than or equal to 0.3 times of MT, total moment. So step 1, calculate eccentricity E to locate the centroid of the pre-stressing steel. That is, next further wherever I use CGS, it is centroid of the steel. Wherever I use CGC, it is centroid of the concrete section. Remember this. So with increasing load, the compression moves upward from the location of the tension T at CGS. A transfer under the self-weight compression should be lie within the kern zone to avoid the tensile stress at the top. See, when you applied the pre-stressing stress at certain section, there will be only compression and there is no tensile stresses or tensile forces. Such zone or such portion we call it as kern zone, and the extreme top point where the tensile stress is 0 and extreme bottom point where the tensile stresses is 0, and only those in between compressive stresses are there. Those 2 points we call it as kern points, upper kern point and lower kern points, and that entire zone is called kern zone of the section. So the lowest permissible location of C due to self-weight is at the bottom kern point, as I said, to avoid the tensile stresses at the top. The design procedure based on the extreme location of C gives an economical section. So the eccentricity what we are going to provide, it should give us the extreme kern point levels. So if you observe the figure, here C and T gives us the compressive stress as well as tensile stress. The tensile stress comes from the tendon. In turn, the tendon will apply the compressive stresses on the section, and here we are considering only MD, moment due to dead load. So CGC, it is centroid of concrete section, and CGS is the centroid of steel or tendon. So the distance between those two centroids is eccentricity. So the shift of C due to self-weight gives an expression for E. So as the position of C, compressive stresses, where it varies, that will give us the eccentricity equation. So that is MD upon P naught plus KB is the distance you can observe in the figure. It is distance of CGC, centroid of concrete, to the lower kern point where the compressive stress acts and the tensile stress is 0. P naught, it is the initial stress, MD moment due to dead load. Here the magnitude of C or T is equal to P naught. The value of P naught can be estimated as follows. So it should be 90% of the initial pre-stress of pre-tensioned member, or it should be equal to initial pre-stress for the post-tensioned members. So how to calculate initial pre-stress? It is area of pre-stressing steel into 80% of strength of steel, what we have assumed earlier. That is the pre-stressing force, initial pre-stressing force. So permissible stress in steel is 0.85 fp, that is 80% of steel, and where fp is the characteristic tensile strength which we have assumed in the first step of preliminary design. So if it satisfies, okay, if it not satisfies, again for that we need to compute the effective pre-stress and area of pre-stressing steel. So here we have considered initial pre-stressing force. So after that we need to calculate what is the effective pre-stressing force and area of pre-stressing steel required. So while solving the problems we can easily understand this. With increasing load, C further moves upwards obviously. Under the service loads, C should lie within the kern zone to avoid tensile stress at the bottom. So what I have told, upper kern point and lower kern point, your compressive force should be between the upper kern point and lower kern point. If it exceeds the upper kern point again, and then bottom fibers will be under tension. If it come below the lower kern point, then top fibers will be under tension. It should not develop any tensile stresses in the concrete as we are designing the type 1 member. So by keeping that condition, C, that is compressive force, should lie within the compression zone. So what is the highest possible location of C due to total load? Is the upper kern point and lower kern point. So upper kern point, when it reaches maximum level of upper kern point, until that the tensile stress will be 0 at the bottom. So what should be that level? For that, again you can observe here, when it reaches the upper kern point, again internal force in concrete will be compressive force. So stress in concrete will be like this. So that is same as calculating the fiber stresses in top and bottom. So by using that condition, if we calculate effective pre-stress, it is mt by E plus kt. Kt is distance between CGC and upper kern point. So here we are considering effective pre-stress as 70% of characteristic tensile strength. So AP is equal to PE by FPE. So here we will get new area of steel required. So for that area of steel, again we need to recompute the eccentricity, same as in previous step. So after that, if it satisfies, continue for further, or if not, again we need to redesign the section. So that is if eccentricity exceeds the limit. For example, if you consider rectangle section of depth 300 mm, so if you assume 25 mm or 30 mm as the cover, the maximum eccentricity allowable is 120 mm. So if for 300 mm section, centroid will be at the 150 level, 150 mm. So below 150 mm, if you assume 30 mm as effective cover, it will be around 130 mm will be, 120 mm should be the eccentricity. So if it not satisfy that condition, again we need to redesign for pre-stressing force, area of steel and eccentricity. Then check for compressive stress in concrete. So the maximum compressive stress in concrete should be limited to allowable values. So the FCK, what we have assumed, it should be in that range. So for that, allowable compressive stresses, it is given in the IS 1343 code book. So at transfer, it should be limited to allowable compressive stress in bottom, and at working stage, allowable compressive stress in the top. So for that, stress in bottom is P0 H by H is the depth of the beam by A into CT. CT is centroidal distance from top. So here if it satisfies the condition A is greater than or equal to P naught H upon FCC, ALL is allowable at bottom into CT. If A is not adequate, then section has to be redesigned. Same case in case of service, at service also same thing. If A is not adequate, again we need to redesign the section. So special case, so in first we have considered MD is less than or equal to 30% MT. Now special case is MD is greater than 30% of MT. So for that, eccentricity should be MD upon P naught plus KB may violate the cover requirements of the beam. So for that we will be having another equation. You can observe here FB equals minus PE by A, P naught by A minus P naught into E minus MD by P naught into CB upon I. On simplifying, the area of the cross section should be greater than or equal to P naught upon FCC allowable into 1 plus E minus MD by P naught upon KT. So let us take one example. Design a simply supported type 1 pre-stressed beam with MT, that is total moment is given directly 435 kilonewton meter, including an estimated MD, that is dead load moment of 55 kilonewton meter. The height of the beam is restricted to 920 mm. The pre-stress at transfer FP 1035 Newton per mm square, and the pre-stress at service FPE is equal to 860 Newton per mm square. Based on the grade of concrete, the allowable compressive stresses are 12.5 Newton per mm square at transfer and 11 Newton per mm square at service. The properties of the pre-stressing strands are given below. Type of pre-stressing tendon 7 wire strand, nominal diameter 12.8 mm, nominal area 99.3 mm square. Okay, so first, what was the data given? Total moment is given, moment due to dead load is given, overall depth of the section it is restricted to 920 mm. So by considering this parameter, we need to provide the width of the section. Then FP, that is characteristic tensile strength 1035 Newton per mm square, effective pre-stressing stress 860 Newton per mm square, FCC allowable, that is fiber stresses at transfer in bottom fibers is 12.5 Newton per mm square, and FCC allowable at top fibers at service load condition it is 11 Newton per mm square. So first, so here the material properties is given, so no bother. MT it is directly given, depth is also directly given here, depth is restricted to 920 mm. So first 4 steps are over because dead load moment is also given, so all 4 steps are given, 5 up to 5th step it is given in the question itself. So next directly we will go for 6th step, calculation of lever arm. Here we need to observe the condition. So 30% of MT, how much it will be? 130.5 kilonewton meter. So the given dead load moment is 55 kilonewton meter. So MD is less than 0.3 times of MT. So that we have to consider second case, that is Z equals 0.5 times of depth. So 0.5 into 920 we will get 460 mm. Then calculation of effective pre-stress, again dead load moment is less than 30% of total moment, so PE equals ML by Z. ML is live load moment, it is MT minus MD, we will get 318 kilonewton meter. So PE equals 380 upon 0.46, that is depth of the beam, sectional modulus of the beam. So it is 826 kilonewton meter. So it is not sectional modulus, it is lever arm, 826 kilonewton. It is the effective pre-stress. So for that effective pre-stressing force, what should be the area of pre-stressing steel we need to consider? So here AP equals FP by FPE. So PE, effective pre-stressing force, it is 826 what I calculated earlier upon 860. It is the pre-stressing effective pre-stressing stress FPE is given in the question. It is 960 mm square. So this is the area of steel required, area of pre-stressing steel or tendons required. So based on that same effective pre-stressing force, we need to find out what is the area of cross section of concrete required. So for that, A equals PE, effective pre-stressing force, upon 0.5 times of allowable stress at service we need to consider, because wherever we will be having minimum stress, that we need to consider when compared to allowable stress at transfer and allowable stress at service. By comparing both conditions, whichever is minimum, that we need to consider. So here 11 Newton per mm square is minimum, so we need to consider that. With respect to that, we will get 150 into 10 power 3 mm square. So it is about 1,50,000 mm square. Then trial section, we can consider this section. Remember, overall depth is 920. You can consider for flanger section, or you can consider for rectangular section, anyone. Here I have considered for I section. You can go with rectangle also. So for I section, I have considered 400 by 100 as the flange size and web thickness as 100 mm. And overall depth of the section is 920. So what we have is, what section we have considered. For that we need to find out what is the sectional properties. So sectional properties, since we have considered symmetrical section, centroidal distance from top as well as bottom both will be same, CT and CB, or you can take it as YT and YB. CT and CB is nothing but YT and YB. So it is 460 mm. Area of cross section, total area required is 1,50,000, but what I have considered is 1,52,000 mm square. So let us check whether it is safe or not later. So for that, moment of inertia we need to find out, radius of gyration, and Kern levels R square. It is R is nothing but radius of gyration, R square by CT or CB, since it is uniform section or symmetrical section. So Kern levels will be 237.41 mm. So in summary of the properties of section and properties of pre-stressing steel, AP we have calculated, and PE, effective pre-stressing force. So next, final design, calculation of eccentricity. So initial pre-stressing force we need to find out. It is APFP. So initial pre-stressing force means it should be under transfer. So 960 mm square is the area we have calculated, and FP is the pre-stressing stress at the transfer stage. So we will get 993.6 kilonewton. With respect to that eccentricity, we need to find out MD by P naught plus KB. We will get 292.76 as the eccentricity. So for that eccentricity, what is the effective pre-stressing force we will get? So for that, MT by E plus KT, on substituting we will get 820.5 kilonewton. So here you can compare with previously calculated effective pre-stressing force PE. Here in concept of moment, we have 826 kilonewton, and after calculating eccentricity and Kern point, we have 820.5 kilonewton. So it is less than previously calculated AP and calculated effective pre-stress. So area of steel and initial stress and eccentricity, all three remain same. If it is greater than previously calculated value, so again we need to calculate the initial precessing force for new area of steel. That is what we have considered P naught for the calculation of AP here. Here PE by FPE is given. So in this case we need to consider new effective precessing force value what we have calculated here. So for example, if we got this as around 830, then to calculate AP we need to consider again 830 by FPE value, like that we need to consider. So then again for that we need to find out what is the initial pre-stress, and again new eccentricity we need to find out. Since we have less than 826, we can keep the same area of steel, initial pre-stress and eccentricity. The number of tendons required, area of the tendons is given in the question itself. It is 99.3 mm square. So AP required is equal to 960 mm square. So for that 960 mm square, total area upon area of each tendon, we will get 9.67. So approximately we need to provide 10 number of tendons. So AP provided 10 into 99.3, we have provided 993 mm square. Required is 960 mm square and provided is 993 mm square. So this is satisfies the requirements of pre-stressing steel or tendons. So tendons portion is over. Now we need to check whether the cross section what we have provided is safe or not. So concrete section what we have provided, whether that is safe for the stress or not, that we need to find out. So for that, at transfer stage, area should be greater than or equal to P naught D upon FC allowable stress at bottom. So that is at transfer stage it is. So allowable tensile stress at bottom into CT. So allowable stress at transfer it is given 12.5, CT 460 for our section. P naught we have calculated and depth is 920, it is given in question itself. So for that it is 1,58,976 mm square. Then at service, allowable stress is 11, same formula, and here we need to consider effective pre-stress. We will get 1,49,181.81 mm square. So you can observe here at transfer stage you have 1,58,000 and at service we have 1,49,000. But the section what we have provided is 1,52,000 mm square. So it is less than area required at transfer. So we need to again redesign the section. No need to go for all the calculations, just write down the comment that the governing value of A is whichever is higher among service and transfer. If you get, if not, this section is safe. So here the governing value of A is 1,58,976 mm square. So the section need to be revised and another set of calculations can be done to calculate the geometric properties precisely. So this comment, if you write, it is enough. It says that the section we need to revise. So this is one example with respect to design of type 1 members. By this, the third module, that is flexural design of flexural members of PSC members, is got completed. So from next class we will start with fourth module, that is shear strength of PSC members. Thank you.